In this video, I'm going to run through a proof of Theorem 1.4 and the Corollary 1.5 that follows from this. You should read through it in the book first, but once you've done that, and if you're still not quite getting it, feel free to continue on in this video. I'll prove Corollary 1.5 a little bit differently than the book. I'm going to prove it by contradiction. Yeah, let's get started. So Theorem 1.4 says that if we sum up the degrees of the vertices, we get twice the number of edges. So I'll start by just saying let G be a graph of order n and size m. And let's say the vertices, actually let's just do it like this. Then the sum of the degrees of the vertices, so degree of v, and I want to sum over all vertices in the graph. So my indexing set here is the vertices of the graph, where v is coming from that set. So v in vertex set of G, I'll write it like this, degree of v. So summing over all vertices, summing the degree of each vertex over all vertices in the graph gives me twice the size of the graph, so twice the number of edges. So why is this true? Well, I'm not gonna write the full proof. You can read this in the book. What the proof says in the book is just that if you sum up the degrees of the vertices, every edge is counted twice, once for each of its incident vertices. And that's really the whole proof. But if you're having trouble understanding that, let me run through an example. So I'm just going to draw a graph of order 5. I'm just going to kind of draw some graph here of order 5. Maybe it's got, I don't know. Let's just draw some stuff here. And let's maybe do this one too. Yeah, let's throw one more in here. How about that? So what this term is doing, this summing of the degrees of v. So one thing I'll do to start this out, I'm just going to write the degrees of each one of these vertices. 3, 2, 2, 4, 3. And I'm going to add those all up. So when I add those all up, in effect, I'm counting the edges that are incident with that particular vertex. So here this has degree 3. So what I'm doing is I'm counting those 3 edges. So that's this vertex done. This vertex, I'm counting these 2 edges because I'm adding up the degree. So this edge in particular between this first and second vertex, this edge has now been counted twice. I'm going to mark that with red if it's been counted twice. And this one's just been counted once. If I move on to this vertex, when I add its degree, I'm counting this edge and this edge. Moving on here, I'm counting this edge, this edge, this edge, and this edge. So now this edge has been counted twice. This edge has been counted twice. This edge has been counted twice. And now I've counted this edge exactly once. So I have this one taken care of. Now moving on to the last vertex. And we'll see what's happening here. Now I've counted this edge twice, and this edge twice. And so you see when I'm done, I've counted every edge exactly twice. And so when we sum the degrees of the vertices, we should get twice the number of edges. Now, this is just an example of that, but you can see why this should be true in general. Each edge is counted twice, once for each of its incident vertices. When I get to that vertex in the sum, I count the edge once. When I get to the other incident vertex with that edge, it's counted a second time. And that'll happen for every single edge, and so we get twice the number of edges. So that's Theorem 1.4 and why that's true. Now, Corollary 1.5 follows from this. That's what corollary or corollary means. I've heard this pronounced both ways, so I'll say it both ways here. But Corollary 1.5 follows from Theorem 1.4. It has to do with even and odd vertices. So remember, a vertex is even if it has even degree, and odd if it has odd degree. So what Corollary 1.5 is saying is that every graph G G has an even number of odd vertices, of odd degree vertices. And this follows, again, directly from Theorem 1.4. So I'm going to prove this, like I said, I'm going to prove this a little bit differently than the text. I'm going to start by assuming, I'm going to say let G be a graph with an even number. Or sorry, I'm going to say let G be a graph with an odd number of odd vertices, of odd degree. So I'm proving this by contradiction. I'm assuming this that this statement is false. That is, we have a graph with an odd number of odd degree vertices. And I'll show you that we arrive at a contradiction. So G is a graph, and so Theorem 1.4 works. If I sum up the degrees of the vertices, I'll get twice the number of edges. So I'll say by Theorem 1.4, the sum of the degrees of the vertices, I'm just going to say V in big V, is twice the number of edges. I should have set up here, let M be the size, G be an even number of odd vertices, let's say of size, or let me say in the proof here, let G be a graph of size M. Remember to always, like I'm doing right now, I introduced, because we always, almost always use M as the size of a graph. I sort of just instinctually wrote M here, but I should define that up here in my proof. And I'll just make a note here, which is even. So when we sum the degrees of the vertices, we get an even number. But G has an odd number of odd degree vertices. So I'm going to say, however, I'll say let E be the subset of the vertices of the graph in V, where each vertex in this set, the subset of vertices, has even degree, or I can just say is even, right? Even vertex means it has even degree, is even. And let O, subset of the vertices again, where each vertex in this set is odd. So we've partitioned our vertices into even vertices and odd vertices. Then, so what we can do here is we can sum up. So twice the number of edges is the sum of the degrees of the vertices. But I can do this sum over my partition. So I can write this as two sums, one where I add up all of the odd vertices, and one where I add up all of the even vertices, the degrees of the even vertices. And this is really all I need. So now I'll point some things out. So this sum, I'm adding up a bunch of even numbers. It doesn't matter if I have an even number or an odd number of even numbers. If I add up a bunch of even numbers, I end up with an even number. So this whole sum here is even. Over here, I'm adding up a bunch of odd numbers. And my assumption that I made was that I have an odd number of odd vertices. If I add up an odd number of odd numbers, I end up with an odd number. And then I know over here, I should end up, when I do this sum, I should end up with an even number. So I have here that an odd number plus an even number is equal to an even number, which of course is false. This is impossible to do. So I'll say, just writing this as formally as I can, since the sum of the odd vertices is odd, and the sum of the even vertices is even, the sum of the degrees should be odd. But we know, but the sum of the degrees of the vertices is even, because it's equal to twice the number of edges. So this is a contradiction. I'll say contradiction. And so there's a little bit more of a detailed proof of Corollary 1.5, which follows from Theorem 1.4. So hopefully that helped you if you're struggling. If not, feel free to ask a question in class, and we'll talk about it. All right, that's it for this one.